Now that we know current 1, we could use a relationship that has both current 1 and another current in it, such as current 2. So let's look at this relationship right here, relationship 4. This says the difference between current 1 and current 2 is equal to minus the EMF of battery 1 over the resistance of resistor 1. So current 2 is equal to current 1 minus, so this means that current 2 is equal to current 1 plus the EMF of battery 1 over resistor 1. We have just found the current I1 to be equal to the EMF of battery 1 over 8R. And then this is plus the EMF of battery 1 over 2R. Let's get a common denominator. And when we do this, we get the EMF plus 4 times the EMF over 8 times the resistance. So for current I2, we get 5/8 the EMF of battery 1 over the resistance of resistor 2. So now we have found an expression for current 2. All we need, and notice that this expression is also a positive result. So what it means is our assumed direction for current 2 was correct. When you look back here, we assumed that current 2 was going into node C. So that's great. Our assumed direction is correct. If we would have ended up with a minus sign in front of our expression for current 2, then that would imply that the magnitude of the current is the same, but it would be opposite in direction. So the only thing we have left now is to find the current through resistor 2. So looking at our diagram, notice we have the currents going into node C, so those are currents I1 and I2, and that has to be equal to the current leaving node C, which we identified as current I3. So I1 plus I2 equals I3. Well, we know I1 was given as the EMF of battery 1 over 8R. I2 was given as 5/8 the EMF of battery 1 over R, and that has to be the current of I3. So I3 is equal to 6/8 times the EMF of battery 1 over R. So in other words, I3 is equal to 3/4 the EMF over R. So let's put all of our results together. We have I3. We have I2 is equal to 5/8 the EMF of battery 1 over R, and I1 is equal to 1/8 the EMF of battery 1 over R. We have now found all of our currents. Now I'm going to leave it to you at home to plug in your values to get the actual numerical values for these currents. Notice that each of these currents have positive signs in front of them. They're all positive currents. So in this problem, we got lucky. The direction that we assumed for the currents are correct. If any one of these would have been negative, then we would have had the same magnitude for current, but the direction of the current would be opposite. The only thing left for this problem now is to find the voltage through resistor 2. And we could do this through a number of different means now. We know that resistor 2 is in parallel with battery 1 and resistor 1, so we could just find the potential difference of that branch. Or we know that resistor 2 is also in parallel with battery 2 and the other resistor 1. So we could find the potential difference of that branch, which would be the same as the potential difference of the branch with the first battery. Or, well, we know the magnitude of the current through resistor 2. We know the resistance of resistor 2. So we could say that the potential difference through resistor 2, and we will say the potential difference from A to C would be the positive current for resistor 2, R2. And again, this positive sign comes from the fact that if we go from A to C, we're going opposite the direction of the current. So this is 3/4 the EMF of battery 1 over R, and this is I3. Now remember, the resistance of R2, we had identified that to be R. So an R in the numerator cancels with an R in the denominator, and the potential difference across resistor 2 is 3/4 of the potential difference of battery 1.